I know one of the things that I pointed out was a bit crap so far was that lots of people just knock up examples of using the MNIST data and don't explain anything that's going on as they try and use it. I've been looking through tutorials online now for 2 days on and off trying to find TensorFlow 2 examples. A whole bunch of the ones I've found don't actually work in TensorFlow 2.0.0. Lots of them are still 1.x, and they've just put 2.0 in the search engine optimizations and things. So it's been a bit of a mess trying to find anything that actually works. What I have done is gone to TensorFlow's website and had a quick look at the quick start tutorials. Let's go through one of those, even though it does do the thing that I was critical of in the previous part of the video. Let's have a quick look at one that uses the MNIST data for handwriting recognition. So let's import TensorFlow as TF, like everybody does. Yep, that's kind of annoying. As TF. And then let's just hit escape. Much better. MNIST. Let's get some data. Let's go to Keras data sets. Keras dot data. In the right spot. Data sets dot MNIST. Okay. Let's get us 2 sets of training data. Or 2 dimensions of training data, X and Y. So let's say X train, Y train, and obviously there's a comma in there. This is a quirk of Python that you can return multiple values from function calls. It's a bit weird coming from other programming languages, but has its advantages. Say we want a set of data for testing, and we're going to get that data from MNIST dot load. Let's do control space dot control space. No, it doesn't know what to do with this. MNIST dot load data, I believe. Okay, now I do know that we need to convert these numbers into floating point numbers, and I believe we do that by dividing them by 255, so FF in hexadecimal. So let's say we want the X data. So let's go X train and X test equals X train divided by 255.0 and X test divided by 55.0. That should convert them to floating point numbers for us. Then we want to use stacked layers for our model. This is a concept that that you see often when you see the models drawn out. You see some kind of hierarchical like flowchart. Each one of those objects in the drawing are one of the layers in the model. So let's create a sequential model. Let's call it model. Makes sense, huh? tf.keras dot jerk keras dot models model dot sequential, I believe. No, capital S. Sequential. tf.keras dot layers dot flatten input shape 28 by 28. So there's 28 by 28 pixels in the MNIST handwriting recognition samples. It's actually a 20 pixel area of interest in the center of a 28 pixel black background. I'm sure you'll have seen them, or you will see them shortly anyway. So we'll go through and have a better look at those in just a moment. So we'll go through and talk about what these actually do when I've done some research in a few minutes, and let's get to the result, and then we'll go back and we'll cover off what flattening the layer does and so on. Let's go tf.keras.layers.dense 28. Whoops, it's going to be 28 nodes in this layer. 128, sorry. Division. I'm also very interested to find out what this means. ReLU. I see that all over the place. I don't actually know what it means, but we're going to find that out as well. tf.keras.layers.dropout. I believe this removes some of the results to make sure overfitting doesn't occur. I believe overfitting is when your model, your algorithm to determine which, in this case, we're going to be recognizing characters 0 through 9. If you make a model that is too good at recognizing the data you train it with, it'll be able to identify everything in the training, or most of the things in the training data perfectly, but the training data and your testing and real life data or evaluation data that you're going to run the model against later are not the same thing, because obviously you're never going to, say if it's handwriting, your handwriting is never going to match perfectly the training data. If the training data and the model are too closely aligned, then the model will be absolutely perfect at identifying the perfect handwriting from the sample data, but not other handwriting. So what we would do with the dropout, I believe, is that we reduce the perfection of our model to avoid that overfitting occurring. Like I say, I don't know all these things, but we will find out as much as we can in a few minutes. Dense is going to be 10 nodes in our dense layer, and that's the model defined. Now I'm just going to hit compile here because I don't trust the IDE to do the syntax highlighting quite correctly. I don't expect this is going to do anything, but I do want to see if there are errors like this. TensorFlow core Keras has no attribute model. Okay, that's all right. Let's check, and that's actually supposed to be models. We hit run again. Yeah, compiled and ran. So we've got a model, didn't do anything, but that's fine. So what we're going to do is take our predictions. We're going to generate a set of predictions for each one of the elements in our training data. So in this X-train, we're going to create a collection of results. So if we've got 5 elements in the X-training data, we want to have 5 locations to store what we think the result is. So we're going to say predictions equals model, open bracket. And we're going to take the X-train. If you're not used to Python, this is going to be a bit weird, but this is how you define slicing of lists, is with the square brackets, and then you can do this, which means take from the start of the array to the 8th position, slice it, split it in that way. In this case, we want to take the very first, from 0 to 1, the first bit out of the array, or the first element out of the array. And we are going to want to store that, in fact, as NumPy data. If we place the debugger here and we run the Python with the debugger, we should be able to see what's actually being stored in this predictions array or NumPy array. So let's have a look here. Of course, you need to, in fact, go one extra line. So Sorry, I just need another line here to step through this line of code. Well, that did not work very well at all. Let's try that one more time. Obviously, changing the code after you've started the runtime doesn't continue. Okay, let's another breakpoint. Let's go to here. Okay, so in here we have a shape. So it's 10 elements. So you can actually see the array there. Oops. So we obviously don't need these either. So it would appear that there are 10 elements in that dimension of the array. Okay, let's move on a little bit. Now I think what we want to do is apply a function that converts these probabilities, these how do I explain this? Because we've got the numbers 0 through 9, so 10 elements, we're recognizing the numbers, 1, 2, 3, 4, and so on. We're going to have their predictions, there's going to be 10 positions to store how strong we believe the model predicts the character we're looking at is of a particular class, a particular type. So each class for us is going to be the class of 0, 1, 2, 3, 4, and so on. And we're going to store the probability that the character that we're currently looking at is a 0, 1, 2, 3, 4. So that's what's going to be stored in the predictions array. What we need to do is use how do I explain this? So this model that we're creating is going to take in a character and it's going to return the probability that it's a 0, a 1, a 2, a 3, or 4. So what we need to do now that we've got the prediction that it's returned, so the model returns from those 10, from the predictions that, sorry, I'm really struggling to try and explain something I don't understand particularly well. We've got a container that holds 10 predictions, 10 weights of predictions. Now we want to turn those into the probability from the original score that the model gives them. So to do that, we actually use what's called softmax. So what we're going to do is say tensorflow.nm, I don't know what that means, softmax, and now we want to take our predictions and we're going to take that and turn that back into a NumPy array. So it's NN neural network operations. There you go. Interesting. Primitive neural network operations. So we're going to turn those predictions back into NumPy array. And actually, it's going to be interesting, I think, to look at this now. So let's do this x equals x again. But this time, what I want to do is actually look at the predictions again. So let's run that. And I believe now we'll get a probability, like a score that says how good a match this particular number is for the model prediction. So the higher the value we get here, the more likely it is to be of a certain type. Because the model hasn't been trained yet, I think the data we get is going to be largely garbage. We're not going to be, our prediction is going to be crap, but what we should see is in here, minimum, maximum. Okay, so there's one of them that there's a 79% chance is a match out of the 10 possibilities. So we're 79% sure, sort of, that that one of these numbers, one of these classes is a match for the input data. We're going to now work out the amount of loss. Loss is the error rate. You can think of this as being almost the inverse of the strength of prediction. At least that's my understanding of it. Could be totally wrong. Sparse, S-P-A-R-S-E, I always spell that wrong. Categorical, categorical. Wow, I don't think I can spell that no matter how many times I try. Let's just cut and paste that out of the other document. Cross entropy. And we're going to take it from the odds of being true to this loss function. So from logits equals true. So this is a log of odds, logarithmic odd of it being correct. This turns it into this turns the results into a likelihood. So we're using the original numbers from here when we do this cross entropy. And according to the documentation, this loss is equal to the negative log probability of the true class. And the loss is 0 if the model is sure of the correct class. So the lower the number we get, the more confidence we have in the prediction. An untrained model gives the probabilities of close to random, so 1/10 for each class. So the initial loss should be close to log of 110, or about the value of 1/10, which is about the value of 2.3. So we should have a loss of 2.3 as the value of each one of the predictions in general, because it's an untrained model and there's going to be an amount of inaccuracy. So now we do this line, and I don't know what this line does. We can figure that out later too as well. So we work out, okay, so we've created a loss function with of the type losses sparse categorical cross entropy from logits. So now we're going to take our logits, our predictions, and we're going to pass them in along with the training data. So in our case, that's Y-train. That's the Y dimension of our training data. So the X dimension is going to be 1 or 0 through 9, and the Y dimension is going to be the sum, or the length of it is going to be the length of the number of training samples that we've got of those 10 classes. So from this we should get the loss of about 2.3 approximately. So it's going to be really interesting to see the value of this. So again, let's do this and check our loss value, see if we get approximately 2.3. Don't know exactly where we're going to see our number here. Loss function. Okay, maybe we're not going to be able to see that 2.3 just yet. Okay, let's say x equals loss function, and see whether we can see if we can get that value out, that 2 or 2.3-ish. Okay, what's the value of x? Okay, no, doesn't do what I expected it to. Not that that's totally unexpected. The untrained model gives a probability of close to random, blah, 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 blah. Predictions dot to numpy. Yeah, I don't know. I would have expected that function to return a value or to be evaluatable to a value of 2 point something-ish. Okay, so now we want to actually compile our model. So we've defined the model here. Now we want to compile the model, and then we want to train it. Or we want to adjust it to fit our data is probably a better way of putting it, I think. Okay, so let's say model dot compile, and we want optimizer. There's an atom optimizer. Don't know what that means. It's the name of it. We've got a loss equal to the loss function. And we have metrics equal to, we want to know how accurate it is. And accuracy is one of the metrics we can determine. I'm sure there are a whole bunch of different metrics that you can return, but let's compile our model. And okay, so let's run this and see what we get if we have a look at this model in the debugger. One assumes I haven't made any typos or logical errors. All right, well, it ran. Okay, so our model is built on float 32s. Our input shape is 28, looks good. And we've got a bunch of layers, 4 of, which are the 4 we defined here. We've got losses, loss weights, loss function, loss. So I would imagine loss weights maybe where we find out how much inaccuracy there is. I'm not really sure. Let's stop the debugger and keep going. Okay, so now what we have to do, we've got a model that's the model's all built in terms of the class, the object is all built. So now we want to actually run it. So we need to do model.fit, because we're going to fit our training data. And so that's our 10 classes, and our ytrain is our depth of pool of training resources, which will be our randomized samples of the handwriting digits themselves, not just the classes. And we need to tell it how many times to run it. Epochs, let's say 8. So at the end of this, we should, and I believe there's something like 50 or 60,000 samples of the handwriting. So at the end of this, we should run through those 50 or 60,000 samples 8 times, adjusting the model each time to make it better and better. So what I would expect to see after we run this is it compiling the fitting the model. So let's actually run the debugger up to the point where we're about to fit the model, and then hit go or step on in the debugger and watch exactly what it does. Okay, so from here I'm expecting to see 8 times it loop through all of the entire Y dimension. Okay, 60,000 elements, and there are 60,000 of 28 by 28 pixels. There we go. So our accuracy is increasing, our loss is decreasing. So we're at 91% accuracy, 95. So this is the model's ability to correctly assign a value to the training data, which is just different from our testing data, which is what we're going to run through after after we've finished training the model. So it looks like we're hovering around 98%. I would expect if we tried too hard here, what we would do is end up overfitting. We would turn the model into a model that perfectly or nearly perfectly can assess the training data, but then when faced with real life data would probably struggle. Okay, so it said we got to about 98.3% accuracy. This is one of the things that I think is missing from all of these tutorials. That's great, but it took us, what, a couple of seconds, a few minutes to fit the model to our training data. We don't want to do that every single time we run through this process. Say if we wanted to recognize a digit from handwriting, we don't want to train the model every single time. We want to take this model and save it. So how do we save a TensorFlow model? Let's have a quick Google and say TensorFlow 2 save model. Keras save model. Load and save models. TensorFlow core. Sounds pretty much like what we're after, I would think. So it would appear that what we have to do after we've created a model okay, that's interesting. Um, I found a way of saving it as the model's being generated. So each time it goes through one of these processes, it would save the current position, but that's probably not exactly what I'm after. I would think I'm probably looking for something a little bit more okay. There's a method to save H5 type models. So now that we've got this model, let's say we want to tf keras dot save model. So the model is going to be model. The file path, we're going to say my model.h5 because H5 models are a thing evidently. Include my say include optimizer equals true and save format equals H5. Don't know if this works, but we're about to find out. So I would expect then in the directory, in our current directory, we would get a file called mymodel.h5 when this finishes running. That took a long time. Let's turn our number of epochs down to 2 for the sake of saving a file. Obviously, when we train the model, we want the best results for our future endeavors when we're using this model, but right now we want to check and see if saving it works. So let's hit run. We should get our 2 epochs. Well, looks like it takes 10 seconds or so per epoch. And in a moment, we should end up with a mymodel.h5, which one would assume you can reload and reuse without having to retrain it every time. Has no attribute save model. Okay, let's find out what that means. see if I can find the instruction manual. Let's have a look. This appears to be TensorFlow 2. Let's just take the entire thing and paste it in there. What could go wrong, huh? So we have a model called model. That makes sense. File path. Let's call it current directory my model.h5. So let's leave this off just in case you're on a different machine. Overwrite true, include optimizer, save format none, signatures none, options none. Let's just assume that all of those work. Seems like they probably do out of the box. Otherwise, this would be a bit of a waste of effort. All right, let's run that. Obviously, one of my settings earlier wasn't making it really happy. Let's do our training. It would be interesting to see how long this takes without the GPU, although the GPU in this laptop is not anything particularly special. It's probably a 5-year-old laptop. Looks like we get pretty good results from 2 epochs anyway. Did we get a file? We sure did, mymodel.h5. Let's open containing folder, open in terminal. It's lsla. Okay, let's try that. Human readable. 1.2 megabytes for the model. Okay, that's interesting. I don't know what I expected, but 1.2 megabytes seems pretty plausible if we've got 95% accuracy for working out a handwriting character. That being the case, let's move on and see what else we can do with this. Okay, so we've done some training, we've saved our model. We're going to assume that we're going to reload the model from the saved one. Let's comment out that line of code. And let's say we're going to well, let's leave all that in there for the moment. We'll deal with the loading of the model later. But let's evaluate our model. So we're going to now say we've compiled the model, we've fit our model, adjusted it to match the training data to get 95% performance when trying to work out what anything in the training data is. So let's pass in the data we separated and set aside for testing. So what I would expect to see here is some degree of accuracy and loss that's printed. I would think we're going to see probably less than the 95% because our training data and our test data are different, and well, we didn't I don't think we over trained it, so we might see roughly 90 something percent accuracy. So I expect to see a number returned for loss and a number returned for accuracy from this function call. Which will be the aggregate of what it got from the training data, from the testing data. Okay, so in fact, we beat our training data. With the separate set of data we used for testing, we actually got nearly 97% accuracy. I don't know how big the results are, the number of samples that we ran through for testing. But we can work that out. Let's just run the debugger up here and see how big the dimension of y test is. There you go, 10,000, which is what that 10,000 must mean. So using one value or for each one out of the 10,000, the average loss was 0.06, and we had 96.8% accuracy. Excellent. One of the things I'm noticing in the documentation is we can actually take that model that we evaluated and then wrap it in this in a softmax layer. So we can now make another sequential probability. We can make a probability model, and we can put our existing model inside with the softmax. And that means we can now pass in um, a bunch of values, a bunch of test data, and we can get the result. So let's pass in to the probability model. Um, we want to take our test data, and we probably only want to pass in a little bit of it. So let's slice that and pass in one value. So this is the first value in effect. And this should give us the probability of all 10 classes. So what we'll get here is a low probability for 9 of them, and then a high probability for 1 of them, which will indicate which class the model determines is the best match. Or at least that's what I expected to see. But it didn't print anything out. Okay, let's run our debugger to here, see what it is exactly that we should get. Now let's see if it actually returns something. Result. Let's see if it returns a value to result, and that might be an array of the probabilities. Or at least that's kind of what I'm expecting. And then when we've done that, we'll work on making this trained model, the saved model from disk, be reloaded rather than training it every time. Okay, result. Okay, it's not really what I was expecting. Shape. Okay, that's a two-dimensional array. So there's 2 dimensions. One dimension has got a value in it, and the other dimension has got 10 values in it. Okay. So it's sort of what we were expecting. So the tensor shape has got 2 dimensions. I don't really know how to turn that into actual data for us though. Maybe if we turn it into a NumPy array. Let's try that. Hopefully this isn't boring you to death. This is probably a whole lot easier if you're the one doing the experimenting, but I'm expecting to see somewhere in this result, I'm trying to turn this into, or trying to extract the NumPy array of results out of this so that we can actually, okay, minimum, maximum. So there's a, we're pretty sure we've got a maximum value here of 0.99. That tells me we're 99.7% confident one of these is a match. So let's have a look and see. Can we see items? This must be horribly annoying for somebody who's very good at Python. Okay, so we've got an array here. Let's have a look. So we've got a very small number, smaller number, small number, another small number. Okay, so if we expand the array, okie dokie, look at this. So it would appear that the class, so these are our classes, 0 through 9. It's just coincidence that their index in the array is also 0 through 9. But if we had classes of A, B, C, D, etc., they would also be listed 0 through 9. But if it was the alphabet, you'd have 27 of them. And obviously, the one with the index of 1 being the second element in the array would be the letter B. In our case, we've got small number, so this is the confidence. Got a very small confidence, small, 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 small. And then we've got one here that says we're 99.8% confident that the seventh class is the one that matches the character that we're looking at. Happily, in our case, it turns out that 0 through 9 is also not only the class index in the array, but it's also the actual the character that we're looking at. So it would appear that the very first character in the testing array of samples is a 7. So that's worth keeping in mind. We'll actually have a look and see what that data looks like in just a moment. But yeah, that's really fascinating. So we've got 99% confidence that we've got a 7. X is not defined. Yep, that's fine because we didn't define it. Okay. So here we did this thing where we saved the model. So let's uncomment that. Let's turn our um, number of iterations, epochs, up to 8 again. And I'm going to run this, pause it, pause the video. I'm going to save this model that's a bit more accurate than the one we've been using. Not that we really need the extra accuracy, but I will anyway. I will save that video and that model, and then we will work on how to load that model without having to train it each time. So if you give me a few seconds, what I will do is I'll kick this off. We can turn that debugging mark off because we don't care about that. Now the epochs are running. I'll pause the video. I'll be back in a moment. All right, so we've run that now through and it's ran for about a minute. We've got our 98% accuracy from our 8 epochs. So this time we've saved that file. It's still 1.2 megabytes, interestingly. From this point onwards, we are working out how accurate this model is. What we need to do at this point is take this line here. So this line is effectively taking the 0th to the 1th element from the testing array and passing it into our probability model to work out which one is the most probable character match. So at this point, what we really want to do is pass in the sample that we want. Because of the way the MNIST handwriting samples are made, they're not BMPs or anything. They're a different format, so we can't just draw one in GIMP or Photoshop and run it through, unfortunately. If I took some time, I could probably write a tool to convert bitmaps to the format that we want, but that's beyond the scope of what we want to do here. So we've saved this my model H5. We don't want to save it again. In fact, when it comes to this, we don't really want to do a whole lot with any of this anymore. We're happy. We've got the model saved. This is our training data. We might keep the data itself because we want to display some of it later. But let's go tf.keras.load model, models, load model. I assume it's load model. Let's have a look. Let's go tf2 load model. Models load model TensorFlow 2. Sounds like that's our baby. File path custom objects compile equals true. Looks like all we need to do is pass in the path. And it was quite simply my model.h5. That should load our model. Should throw a import error or IO error if it doesn't work. Wonder if we need to compile this model or not. It'll be interesting, won't it? Let's say model equals. Let's try running that. We should get the same results as before, but this time we won't have to run all the epochs to train it, if this works. Bam, there we go. We got our 97% accuracy on our test. So this passed in one of the values, worked out what the value was. Again, we're expecting the value to be a 7 because we ran this one before with the previous code. But let's just open up that results array. So this time you notice it was much quicker because it didn't have to train every time. Let's check out our results. That's very annoying. Interesting to see. Actually, what we should do is print through that array. This is probably going to just dump some horrible value to the console. Okay, so now we have our result. It's a float. It's an array of floats, sorry. And let's have a look at the array. So again, 99.9% confidence this time round. So for interest's sake, let's pass in the next character. See what the second character in the testing data is. See if we can predict with some degree of confidence what it is. Let's have a look at our results. Data type, oops, wrong one. Array values. This time we're 99.90% confident that it's a number 2. So it would appear that our model is well trained. It, and obviously 2 samples doesn't, like two sunshines don't make a summer. That's a pretty weak test, but interesting nonetheless. So now, instead of retraining the model every single time, we've saved the model to a file. Now we're reloading the model each time we want to use it. So I think that makes a fairly natural stopping point. What I'll do is I will stop and I'll create another video that shows us the MNIST data set so that we can actually have a look and see what value those first 2. So we had a 7 and a 2 were our first 2 numbers. Let's make some mechanism for loading those pictures up on the screen, and I think we're going to be using pyplot from memory. All right, I'm going to bore you just a little bit longer. Let's plot out those first say 2 elements of our MNIST data. So we're going to start by saying import pyplot. Let's just run that, make sure I've got pyplot actually. No. So from matplotlib, I think. Yes, okay. All right, we don't want to, we can print those results. We don't really care about that a hell of a lot, but let's print those results. And let's say we want to, for I in range 9, because there are 0 to 9, so 10 characters. Let's say pyplot subplot, yeah, 280, 10 times the pixel size of the images, stretch them 10 to 1. Plus 1 pixel for the border, and the position. So this will create a second plot inside the first plot to show the actual little widget, the character itself. And I think what we want to do is go pyplot .imshow. No, we want to say our test x data, and the first one, let's say, we're going to use I, the counter, so we're going to see 0 through 9, so 10 elements. So if we did this correctly, the first one will be a 7, the second one will be a 2, and we don't know what the next one is, but we could test that. In fact, we're going to see. And then it's comma C map equals pi plot dot get C map grey. So this is building our grid of results. Now what we want to do is show pyplot dot show. Show. All right. So if this works correctly, that doesn't look like a winning start, does it? I don't believe that. Test X is defined. So compile and see. That particular kind of error in Visual Studio Code is a bit confusing. Object is not callable. Pyplot. Okay. Yes, no, I need to refer to it as pyplot.subplot. Yes, because we need to show the subplots inside the other plot. Oh, it's not test X, it's X test. Let's run that. That's better. Okay, so what I'd like to see now is a plot of 10 or 9 characters. Map plot figure 1 is, there we go. All right, look at that. 7 and 2 were our first characters. Now if we wanted to say, you know, this one's a 4, so this is going to be interesting. When you mouse over, you can see the value inside. So 0 being black and 1 being white. So the whiter it is, the closer to 1 it is. Cool. Okay, so the value of the fourth one looks like a 0, or maybe a 6, depending on how optimistic we are. Well, in particular, this one. This one looks hard to work out. Let's see how confident we are of predicting what this is. So this is going to be our 10th one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Our 9th one. Let's have a look at number 9 and see what number we get as a result. So this is going to be 8 and 9, I believe. It's going to give us our 9th one. So this time, instead of, I don't think we can do it quite like that. Let's have a look and see what number we come up with this time. Okay, so we've got a result. Our array down the bottom here indicates we've got a low, 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 low. Okay, so we don't have a great deal of confidence here. Let's have a look at our result. Let's look at our array. -11, -6. Okay, so we're 87% confident that was a 5. Now that did actually look vaguely like a 5. We happy that's a 5? Frankly, being 88% certain that's a 5 is good going. I'm not even that certain. Okay, so hopefully that's given you some ideas of things to look at, a couple of ways of going about doing things, and a little bit of an introduction to how TensorFlow 2 and Keras works. And like I say, I'm not an expert in this. I'm not even a very good Python programmer. I think it is really interesting. There's clearly heaps and heaps of power to be had. I mean, it took us, what, 2 minutes to train a model that's 88% certain that this rubbish is a 5. that's, to my mind, that's pretty good going. If you wanted to use this to, say, read the digits off a form that somebody's written in, you would have to take a photograph of the form, process it with something like OpenCV, and then you would need to determine which is the region of interest that you wanted the numbers from. Then you would have to separate each one of the individual characters into an image, scale it to 28 by 28 pixels, which is what our MNIST data is, and then turn it into a black and white, turn the character, probably invert it, if it's on a white background, invert it, work out the white area versus the black area to create the individual character, center it inside the 28 pixel by 28 pixel black square, or black once you've inverted it, and then you would have to pass that image in the correct, in the correct data format into this line of the code. So instead of passing in, the ninth element from our X testing data, you would pass in, my character number one, number two, number three, for the first, second, third characters off the form. And for each one of those, you would get a level of confidence, and you would also get from being able to determine which one of the 10 classes you thought the character was and how confident you were, you could come up with, say, minimum and maximum and standard deviation of confidence for the entire string of characters. And you could say if you're 95% confident on average of the numbers, and none of them are more than 5 or 6% from deviation from your average, that you're pretty happy that you're within sort of 90-ish% that every one of those characters is correct. You could then automatically process that. And if it fell below, say, 75, then you could pass it through a second process, or you could have a human intervene and determine what the characters are, for example. So that's how you would turn this theoretical piece of code and us playing into something that was more practical. There's more steps to it than just loading the MNIST data, training a model, and then hitting compile, and away you go. You still need to do the image processing and the separation and taking out the relevant data from your image source or your video or whatever it is that you want to process, and pass it into this model and um, evaluate the results of the individual character you want when you're not being given characters from a scanned copy of a form, for example. Anyway, I hope that was vaguely interesting and I didn't bore you to death too much with my spelling errors and waffling. Let me know if there's some part of this that you're particularly interested in, and otherwise I'm just going to sort of muddle along on my own.